Welcome to lesson 4.8. Triangles and coordinate proof. Okay, let's see how we did on the warm-up. The directions say determine if the triangles below are congruent. If yes, indicate which postulate, side, angle, side, would prove them congruent. All right, so in number one, the only thing that is shown congruent are these pairs of angles, but I do see that they share this side. So technically that would be congruent to itself. And we could use angle, side to prove that both of those triangles are congruent. Similar problem in number two, where they share this side, that'd be congruent to itself. So that one you should have said set aside. In number three, we have another shared side. However, if I want to use side, it has to be the included angle, and it is over here, but it's not over here. So they're showing me that two different angles are congruent, so that one was actually none. Okay. Number four, they're showing me these sides are congruent. And then I have a pair of vertical angles here, so even though it's not marked, I need to recognize, hey, those are vertical angles, those would also be congruent. And then we can use side, angle, side, SAS. 5 is kind of a tricky one. If you said none, I would give that to you because, we know this side is congruent, but we don't know the included angle. However, if you recognize that we do have like this big isosceles triangle here of these congruent side, technically these angles would be congruent. These angles would be congruent also. Okay, if you can kind of picture that green, that big one. And then we could say, well, this would also be 90 degrees if this is 90 degrees too. Then we could say like angle, side. Yeah, I got the angle, side. You could do that. But if you said none, that's totally fine. That was kind of a tricky one. Angle, side technically. Number 6 I really like. So they're showing me I have two congruent sides. There's a couple different answers you could have. The other thing they're showing me is that these lines are parallel, which means we have some alternate interior angles here. Okay, if these lines are parallel, let me extend them. This could be a transversal, meaning this angle and this angle, alternate interior angles to be congruent. Same with these ones. This one and this one on this transversal. Or you could have said the vertical angles. So on this one, you could have used angle, side, angle. Or you could have used angle, side if you used the vertical angle. I would accept either of those answers. However you see that. But make your markings in there. Like show like the sides congruent to this. Show those angles are congruent because that can help you identify which postulate we're using here. All right. So that's a review because today is the last lesson in chapter 4. Can you believe it? They don't seem too enthused. I thought you guys would be more excited. We're almost done with the triangle stuff. Okay. Well, this lesson is kind of weird. I don't really classify it as like challenging. It's just a little like different. And it involves something called a coordinate proof, which is just basically nothing fancy. And you're just kind of like showing your work. It's a very unorganized like type of proof. All right. So let's kind of talk about what it is first. Basically, you're just going to place shapes, and we're going to mostly do triangles, obviously, because that's what chapter we're in. But this works for any geometric figure. You're going to place it in a coordinate plane. That's like your XY axis. Okay. And we're going to do some algebra, tie in some algebra to prove certain aspects of like isosceles triangle, right triangles, equilateral triangles, all that good stuff. So we're going to use some other like kind of like formulas or previous concepts that we've talked about. We'll list them out in a second. But basically, we also use like variables. That's the part that's kind of weird is we don't use like numbers for these coordinates because we kind of place them wherever we want. And we use variables to represent like these distances so that it can be applied to like any triangle in the coordinate plane. All right, that's basically in a nutshell what a coordinate proof is. All right, here's what we are going to use in this lesson that we've learned before, but we're going to jot down as a little refresher. Okay, first thing, we're going to talk about parallel and perpendicular lines and what we know about their slopes. Ooh, been a while since we talked about slope. All right, first of all, who remembers the little like formula for slope? How do we calculate slope? Hear some things. You can shout out loud, Jessa.
y2 minus y1 over x2 minus x1.
Perfect. Changing y over changing x, right? Good. That's how we calculate slope. We're going to need to do that in this lesson, so don't forget how to calculate slope. What do we know about parallel lines and their slopes? They're the same slope, right? They're the same slope. What about perpendicular lines? Reciprocal, what else? Opposite. Good. Thank you, Matthew. Opposite. Reciprocal. Slopes. All right, so that's going to come back. We may have to show that we have like congruent lengths. So maybe like, okay, equilateral triangle, show that all the sides are the same, or isosceles, show that too. Any idea of how we might calculate the lengths? Which formula? Distance. You know it. Don't forget about it. Distance formula. So that is the square root x2 minus x1 squared plus y2 minus y1 squared. Ooh. Last one. It's been a while since we've done this one. The last one we're going to use in this lesson that we've done before is the midpoint. How we calculate a midpoint of a line segment. Anybody remember that formula or how we calculate that? Ooh, Ben?
Is it x1 plus x2 divided by 2 plus y1 plus y2 divided by 2?
Nice job. Nobody in Centaur remember that. Nice job. It's just halfway between the x coordinates, and it's obviously like on a coordinate plane. This also works on a number line for just like the x. Halfway between the x coordinates, and then if we're talking about a coordinate plane, halfway between the y coordinates as well. That would give us the middle of a line segment. Okay, so we're going to use a bunch of those in some of our proofs and practice problems today. The first thing we're going to practice, we'll make sure you have the right formulas down. These are important. All right, first thing we're going to practice is just placing a triangle in a coordinate plane. So here's some tips. And this isn't the only way we can do it. And that's why we are going to use variables that give us just like general values of the coordinates and not exact numbers. Is because we could technically place a triangle anywhere we wanted to on a coordinate plane. But here's the easiest way to do it. Place one of the vertices of your triangles at the origin. Okay? What's the coordinates of an origin? 0, 0, right? So it gives you easy numbers to work with. And then place any sides of your triangle that you can on the x and y axis, because again, those include zeros. Like your x and y intercepts have zeros in them, so easy numbers to work with. Try to keep everything in the first quadrant, and that just keeps everything like nice and positive. Okay, so you can see for these practice problems, I just sectioned off like the first quadrant. All right, so let's try one here. This one, first example says, position and label a right triangle XYZ with leg XZD units long. So here's a good first example of using a variable instead of like actually numbers on the coordinate plane. So the first thing you want to do is go ahead and place one vertex of your triangle right at the origin. So put a point there. Now, it's a right triangle, so we know what that looks like. It looks something like this, a right angle. So it says that the leg, one of the legs, is XZ. They're talking about one of these lengths. Okay, what do we call this one? Hypotenuse. Okay, so I can't draw my hypotenuse D units long. It says one of the legs. So I'm just going to keep it easy. I'm going to call this leg XZ. So I'll call this X and I'll call this Z. All right, now they told me this is D units long. So the only other thing I know is that this is a right triangle, which means I'm going to want to draw its other leg perpendicular to this leg. So if this one's on the x-axis, where is my other point going to be? On the y-axis, right? That'd make it perpendicular. Somewhere up here, there's my other leg, and then you can draw on your hypotenuse. And again, the position doesn't matter. We're going to use variables to describe like just the general coordinates and how this could work for any right triangle we draw here. Let's also label in a right angle so we know this is a right triangle. Okay, so it says position. We did that, but it also says label. So when it says labels, they want you to give the ordered pairs. So you can either do that right in the picture if you want, or some people like to do this off to the side here. Make like a list. X is easy because we placed it at the origin, so we're going to call that 0, 0. And that's why it's easy to do that, place it at the origin. The other one I can figure out is Z, because I know this distance of this leg is D units. All right, now picture if this was a number. Say this was 6. That means the ordered pair of this point Z here would be 6, comma 0, right? Because I'd move 6 on the x-axis and 0 up or down. So it's whatever D is, comma 0, since it sits right on the x-axis. So there's Z. Now Y, I don't necessarily know what its y coordinate is, but I do know what its x coordinate is, right? If I were to plot this point, the x coordinate would have to be what? 0, right? That'd be the only way I could end up on the x-axis if I move 0 left or right. And then they didn't tell me anything about this side. Did they say it was isosceles, that these would be the same length? No, they didn't. They just told me it's a right triangle. So here's the fun part. You get to pick any other letter you want. It just can't be D. So I picked A because I'm bored. I usually pick A or B. So I just pick A, and again, that just gives us the general coordinate of where that would be. It'd be 0, comma some value, and you can write this in your notes, any letter except D. All right. So again, you don't have to do this. If you just want to label them right in your work, I'm fine with that. Let's try another one. This one says position and label an equilateral triangle ABC with side BC W units long. All right, first things first, I'm going to put one of my vertices here. Now, when I see this side BC W units long, I usually place side BC on one of my axes. Okay, and I usually do it on the X. So I was like, all right, I'm going to call this B. I'm going to call this C. And then I know this is W units long. You could write that inside your triangle. You could write it outside your triangle too if you want. Maybe that would look better actually. Put it out here. All right, I know this is an equilateral triangle. So my vertex is going to be somewhere up here. I know it's called A, since it's triangle ABC, and then I know it's equilateral, so try and make your sides as congruent as you can. Okay, it's not a right triangle, it's equilateral, meaning all the angles are 60 degrees. All right, let's find the coordinates of everything. Let's start with B. What would the coordinates of B be? 0, 0. They're right at the origin. We did that on purpose. The next easiest one is probably C, since this is a distance of W. It's going to be W, comma, what, folks? 0. Exactly. All right. Now, A. Because this is an equilateral triangle, folks, this vertex, if you were to kind of draw a line down here, this vertex is always halfway between the base. All right? We'll dig more into why when we get to special right triangles and we do some trick stuff. But all you need to know for right now is anytime you have one of these equilateral triangles, this vertex, because all the sides are congruent, is always halfway between that other side. Okay, just like point C would be halfway between A and B also, okay? So we actually can figure out the x-coordinate of point A, because if this is W, I know it's halfway between W, so you could either say half of W, or I often do this, it's whatever W over 2 is, W divided by 2. So we know the x-coordinate's halfway. However, we don't know the height. So that's when you get to just pick a letter. What did I pick this time? B. And that could be any letter except a U. Okay. They're kind of weird because, like I said, it's a lot of letters, but once you practice them, they're not too hard, and a lot of the problems end up looking the same. All right, the next set of practice problems, these ones are fun. It's kind of like a puzzle. They positioned a triangle for us, and then we have to find the missing coordinates. So in this first one, it says, name the missing coordinates of the isosceles right triangle. Right triangle, because it's a 90-degree angle. Isosceles, meaning two sides are congruent, and it's obviously not going to be a hypotenuse, so it's going to be these two sides. All right, so I have missing coordinates Q and missing coordinates S, but they give me R. All right, Q, that's easy. Where's that one? 0, 0, it's at the origin. It's at the origin. Come on, folks, stay with me here. Okay. R is C, comma 0, meaning this distance is what?
C.
C, good. And if this is an isosceles triangle and this segment is C, what's this distance going to be? C, also C. So what's the coordinates of S? C, comma C, yep. C, comma C. The variables are just standing for that this would work for any isosceles right triangle positioned anywhere with whatever C is. If C is 10, S would be 10, 10. Okay, that's what that means. All right, let's try a couple more. Name the missing coordinates of each triangle. This one's showing me that I have an equilateral triangle. X, they gave me, was at the origin. Y is 2b, comma 0, meaning this distance is what? 2b. They want me to find Z. Well, I know since it's up here, it's exactly halfway from that base. So what's half of 2b? B. We know the x coordinate's B. However, I don't know what the height is, so we're just going to call it any letter except B. I called it A. There is a way to actually calculate what it is, but we'll learn that later. Okay. Last one. Here I have an isosceles triangle. They're telling me S is negative A0, so we're dipping over here into quadrant 2. That's okay. If this distance is A, it makes sense that U is at A0. I need to find T. All right, what's the x coordinate, obviously, of T? 0, right? It's right on my y-axis, 0. Okay, now here's like a good one to kind of picture, like, sometimes we're like, when do you just get to decide to pick a letter? Picture, like, couldn't I drag this vertex, like, up here, and it would still be an isosceles right triangle if I kept these two vertices, S and U, if I kept them parked right here? I could, like, move T down and still have an isosceles triangle, or I can move it up. So that, like, height is interchangeable. Like, it can be anything. So that's when you can just pick a letter. We don't know. There's no, like, defined exact height there. So this time I picked B again. Anything except A. You could use C if you want to. We just can't use A because that was already used. Okay, I can't use B here because that was already used for other lengths in my triangle. Okay, those are kind of fun. A lot of them involve zeros because a lot of them are on the axes. All right, we're just going to do 2 proofs. This first one says, write a coordinate proof to prove that the segment that joins the vertex angles of an isosceles triangle to the midpoint of its base is perpendicular to the base. Okay, I'm going to start by just drawing an isosceles triangle. Not a right triangle, just an isosceles triangle. And I'm going to say these are my 2 congruent sides for this proof. So what they want me to prove is that the segment that joins the vertex angle, that'd be this angle, to the midpoint, I'm going to call it M, to the midpoint of its base is perpendicular. All right, I'm going to put some letters on this vertex to help with my proof. So I'm going to call it A, B, C. I'm also going to label these with their coordinates. A is obviously 0, 0. Now for this proof, we get to kind of pick what we call the distances of these triangle lengths. All right? Now, if I have to calculate the midpoint of something, I want to pick a number that's even because I can easily figure out what's halfway between. So what I'm saying is, like, don't call that distance 1, because then if you have to find the midpoint or halfway between 1, you're working with fractions now. So I'm going to call it 2, and I got to throw in a variable there so it works for anything. I'm going to call it just 2b, or you could say 2a. I actually did 2a in the other example. It doesn't matter. I'm going to call this distance 2b. That distance is 2b. So C would be 2b comma 0. B, we know that vertex angle is halfway between the base there. So that would be B, comma, something other than B. I'm just going to call it C, some height. Okay. So these ones are kind of weird because you got to come up with a lot of the letters yourself. First thing we need to do is calculate the midpoint of this line segment. I know a lot of you guys could figure this out without doing the formula, but this is good review over the midpoint formula. How I'd find the midpoint of AC, this segment, is I add the x coordinates, so 0 plus 2b, and divide it by 2 halfway. And add the y coordinates, 0 plus 0, divide those by 2 to figure out halfway. So the midpoint, 0 plus 2b is 2b, 0 plus 0 is 0. 2b divided by 2 is b. 0 divided by 2 is 0. All right, so that midpoint is b0. So again, the reason why I picked 2b was because I got a nice, clean, no fraction midpoint. I'm going to call it n. All right, now what we're trying to prove, folks, is that red segment, the one from the vertex angle to the base, is perpendicular to the green segment. So the way I'm going to show that they're perpendicular is I'm going to calculate their slopes. And if I can show that their slopes are opposite reciprocals, that means those lines are perpendicular to each other. And again, here's another one, like you could figure out what the slopes of those lines are without doing the math here, but let's find the slope of the green line first. Slope of AC. Change in y or change in x. So y2 minus y1, 0 minus 0, over x2 minus x1, 2b minus 0. We get 0 over 2b, which is 0. We know that. What's the slope of horizontal lines? 0, right? That's what I'm saying. You probably could have figured that out without doing the math, but it's good practice. Okay. Let's find the slope of the red segment, BM. All right. Change in y, 0 minus c, all over change in x, b minus e. I get negative c over 0. Uh-oh, what does that mean? Undefined. Thank you, Matthew. Undefined. So though it's not as easy to see these opposite reciprocals, we know that horizontal and vertical lines are perpendicular of each other. So that's enough to show, and we did this with like what's called technically a coordinate proof. We're showing all this work with the coordinates. There's no like steps and reasons and statements and all that stuff. So yes, BM is perpendicular to AC, and I just put maybe opposite reciprocal slopes right here. Okay. We need everybody to pick their head up, please. We got one more, people. One more, and then notes are done for a while. Actually, a whole week. All right, one more coordinate proof. This time they want us to prove, and look at, they placed all this for us, and they did all the labeling of the variables for us. This time they want us to prove that triangle ABX is congruent to triangle CDX. They want us to show that these two triangles are congruent. They didn't give us anything. No markings of congruent, no markings of parallel lines. What jumps out to me right away is I do have a pair of angles that are congruent. Who sees it? Gwen? The vertical angles, these ones. Good. So we can state that right away. That angle AXB is congruent to angle CXD, and you can just say by vertical angle theorem. Okay. What might help us, and if I look at X, doesn't it kind of look like it might be a midpoint? Because I see it's divided by 2. All right, so what we're going to do is we're going to calculate the midpoint. I'm just going to start with BD. You could do AC first. Doesn't matter. Let's see if X is the midpoint of BD. So we're going to find the midpoint of BD. All right, so I got to add the X coordinates. So I have 0 plus X for the X coordinate on B plus A. I got to divide that by 2, comma, add the Y coordinates, which is just be B plus 0 over 2 All right, let's simplify that a little bit. 0 plus x plus a. Normally, we'd probably write the a first. Usually when we write variables in math, we write them in alphabetical order. So I have that. B plus 0 is just b. And I'm like, hey, x is the midpoint of BD. And since x is the midpoint, of BD, what does that tell me? What does the definition of a midpoint tell me? What'd you say? What are congruent? Thanks, Glenn. Bx is congruent to xd, exactly. All right. We're going to do the same thing for AC. You'll see that it's also the midpoint of AC. Almost done, folks. Hang in there. All right, midpoint of AC. I do 0 plus a plus x. Add the x coordinates. Divide it by 2 to figure out halfway. Add the y coordinates. 0 plus b. Find halfway, or like this feels oddly familiar. We get the same thing because x is also the midpoint of AC. Nice, meaning these two segments are congruent. So, since x is the midpoint of AC, AX is congruent to XC. Is that enough to prove the triangles are congruent? Yes. By what? Side angle side. SAS. Side angle side. Side angle side. So that's what we want to state. Triangle ABX is indeed congruent to triangle CDX by side angle side. Boom. There you have it. That is chapter 4, my friends.